Hi, good morning everyone. My name is Hugo Salgado. I work for NIC Chile, the .cl registry. And first of all, I want to apologize for not being there in person, but I want to thank David for this opportunity to show our work. This presentation is about the threshold cryptography project that we're working on from like 4 or 5 years, and how we envisioned can help to the root signing process. First, some words about the threshold crypto project. What we have is a working solution to replace a real HSM with a virtual one using threshold cryptography. By this way, what we accomplish is to provide a robust and distributed way to do DNSSEC signing. Robust in the sense of not having a single point of failures, and distributed by being able to separate the signing in several pieces. All of this without having to sacrifice security. In this diagram, we see how it works in a high-level view. In this part of the diagram, from points 2 to 6, we are replacing an HSM in the normal way of the signing process. Here we have two separate objects. First, we have the signing dealer, a trust entity who orchestrates the nodes, merge their output, and verify the process. And we have several nodes which owns a piece of private data and carries the signing. Before being able to sign, we need a one-time setup of the network where we create a normal RSA key with its public and private parts, but then we generate from this n other subkeys, each one also with public and private parts, that have the property of being able to generate sub-signatures that can be combined with a special algorithm to regenerate a new signature that corresponds with the original public key. So by this way we can delete the original private key and operate only with the sub-key parts, with the public key and the combining algorithm. So in normal operation we start with step 1, where we have a resource record we want to be signed that is delivered to the signing dealer. This dealer then sends this data to the end nodes in step 3. Afterwards, in step 4, each node uses its own subkeys to sign the data, creating sub-signatures. In step 5, they deliver these sub-signatures to the dealer, which in step 6 first verifies each one, then waits for having a subset of m sub-signatures, and then merges them. The result then can be verified with the original public key using normal crypto operations, and then in step 7 the result is returned. After all these steps, we have a normal DNSSEC signature which can be verified by everyone with access to the public key. We have a private API to control the process, but also we developed a PKCS 11 interface so we can expose the HSM to normal DNSSEC control software like OpenDNSSEC, Keynote, Bind, etc. The code is open source and you can download it from here. We also created some Docker instances to just try it which are integrated with two popular signing software. But now, how can we use the threshold cryptography for DNS root signing? First, a recollection on how the signing currently works. The root signing ceremonies are carried 4 times a year, each one in one of 2 physical meetings. Each one lasts 4 hours approximately and needs around 15 people, including at least 3 trust community representatives from around the world, the TCRs. This is needed because in normal asymmetrical cryptography operations you need to have access to the private part of the key escape, which needs to be stored in a secure place. The current method hides the private part inside an HSM that needs to be accessed by M of n other HSM keys. The trust community representatives hold physical keys that are needed to unlock safes where these M of n HSM keys are stored. In this diagram, I wanted to summarize the process. At left side, we have the minimum 3 TCRs that travel to one of the ICANN facilities with their physical keys, which combined with second physical keys held by ICANN staff people allows to open the safes, collect the HSM keys, unlock the actual private key inside the HSM, and with the data as input we can generate the final signature. What we propose is to distribute the signing of the data, not to distribute the key, but distribute the signing process. As I said before, after the original setup ceremony, there's no need for a private key, only special craft subkeys. After that, there's no need for a physical ceremony, because everything can be carried remotely and asynchronous. Also, there are methods to verify each sub-signature, to discard more than M subkeys, and to detect certain kinds of adversaries' attacks. Even when the dealer needs to be a trusted part of the process, we can have external witnesses that can verify each part of this process. And at last, the output of the process looks like a normal signature, verifiable worldwide. So we end with a diagram like this. We don't need a globally coordinated physical ceremony, but maybe we can use local ceremonies for each part of the subkeys signing. We can use existing technologies for secure communication channels between the dealer and the nodes, like TLS channels and PKI certificates, which can be coordinated at the same first setup ceremony. So the benefits are clear: decentralization, end of global physical meetings, and broaden the participation on the root KSK signing. But also we know this introduces new risks that have to be identified, studied, and mitigated. And that's what we are working right now. And that's where we think the Yeti people and infrastructure can have a key part.
Yeah.
First of all, we need to write a high-level document of this proposal, identifying all the benefits and new risks. This document should be written in such a way to be discussed with ICANN people, not only technical ones, but with policy people too. Then we're currently working in enhancing our software and to create stress tests with high number of nodes, M and N figures, and also with adversaries. In this point, we're working also in a cryptography study from the math side of the crypto to study the optimal numbers of n and m, knowing that these numbers are critical from a policy point of view. Also, we want to create a risk matrix showing the shift of risk from a single key to multiple subkeys. And of course, prepare and carry several testbeds with Yeti. Okay, that's all. I personally feel this work should be carried on. I know this proposal can be controversial in many ways, but I think it's worth to be tried and at least be properly documented and discussed. So, thank you. I will be remotely available from now to hear your comments and maybe questions. Thanks.